All right, today we're going to go on a pretty wild journey, a microscopic one, to follow the path of a single electron. And why are we doing this? Well, it's because understanding its simple one-way trip is the absolute key to understanding direct current, the fundamental force that powers so much of our modern world.
So think about it. We throw around the word electricity all the time, but what is it really? When you get right down to it, it's all about movement. It's the controlled flow of something incredibly tiny and incredibly numerous that makes, well, everything from our phones to our cars actually work.
Okay, so here's the game plan for this explainer. We'll kick things off with the basics of what electric current even is. Then we'll zero in on direct current, or DC. We're even going to learn how to calculate it, understand why it can be dangerous, and see how the pros measure its flow.
So let's dive right in. Think about it. Every single device you rely on, from your computer to your fridge, works because of one simple principle: the transfer of electrical energy along a wire. And that transfer? It has a name: electric current.
So what's actually going on here, down at the atomic level? Well, inside a conductor like a copper wire, some electrons aren't really attached to their atoms. We call them free electrons. When you connect a power source, it's like it gives these free electrons a giant shove, forcing them to march in one organized direction. That organized march is the electric current.
So, to boil it all down, electric current is just the movement of electrons. This movement carries the energy that powers our world. And the logic here is super simple. The more electrons you have marching past a certain point, the greater the current is.
All right, so now that we know what a current is, let's get a little more specific. There are a few different types, but today we're focusing on the simplest, most fundamental kind, the one that early scientists first figured out how to use: direct current, or as you probably know it, DC.
The name really says it all, right? Direct current. Just think of it like a one-way street for electrons. They start at the negative end of a power source, like a battery, and they flow in one and only one steady direction toward the positive end. No U-turns, no going backwards, just one way.
Okay, so we have this flow, but how do we measure it? For that, we can thank the French physicist André-Marie Ampère. His work back in the 1820s was so groundbreaking that the unit we use to measure the intensity of a current was named right after him, the ampere, or just amp for short.
So just how many electrons are we talking about here? Brace yourself, because this number is absolutely mind-blowing. A current of just 1 amp means that 6.2 quintillion electrons are zipping past a single point in that wire every single second. Let me say that again. That's over 6 times billion electrons. It's just an insane amount of traffic on that tiny one-way street.
Okay, so that invisible flow of quintillions of electrons might seem totally mysterious. But you know what? It's not. It's actually incredibly predictable, and we can calculate it with perfect accuracy using a formula that's surprisingly simple.
And this right here is the key to it all. The formula is beautiful. I equals Q divided by delta T. Now, that I stands for current, which is a little nod to Ampere's original work on the intensity of the flow.
So let's break that down real quick. I is our current, measured in amperes. Q represents the total amount of electric charge, which we measure in something called coulombs. And a coulomb? Well, that's just the name for that huge group of electrons we were just talking about. And finally, delta T is just the time that's passed, measured in seconds.
All right, let's put this into practice and see how it works with a real problem. Let's say we have 0.85 coulombs of charge passing a point, and it takes 2.5 minutes. The question is, what's the current in amperes?
Okay, this is actually a really straightforward process. First, we just write down what we know. The next step, and this is super important, you can't forget this, is to convert our time into seconds. So 2.5 minutes becomes 150 seconds. Now we just plug those numbers into our formula, 0.85 divided by 150, and we get our answer. The current is 0.0057 amperes. Simple as that.
So we've covered what current is and how we can calculate it, but now we need to talk about something just as important, and that's why you have to respect it. Electricity is an incredible tool, but it can also be incredibly dangerous.
And here's why this matters to you personally. See, your whole body, your nervous system, it runs on its own tiny, very precise little electrical currents. Every thought you have, every move you make. An external shock from a wire can completely overload that delicate system, causing all kinds of problems, from muscle spasms to serious injury.
And just look at this table. It is shocking, no pun intended, how little current it takes to be dangerous. Less than 1,000th of an amp is just a little tingle, but you can see how quickly it ramps up. By the time you get to just half an amp, It can be enough to mess with the rhythm of your heart. And that is exactly why you always see professionals being so careful and cutting the power before they get to work.
With that in mind, how do electricians and engineers actually measure this stuff safely and accurately? Well, they use a special tool, and maybe even more importantly, they use a very specific technique.
The tool is called an ammeter. It's built for one job, measuring amperes. But there is one absolutely critical rule you have to follow when you use one. To get a good reading, that ammeter has to be connected in series with the circuit.
So in series just means the ammeter becomes part of the main path. Remember that one-way street analogy? Connecting in series is like putting a toll booth right in the middle of the road. Every single electron has to pass through it, so you count all of them. But if you connect it in parallel, like you see on the right, you're basically creating a detour around the toll booth. The current will split, you'll only measure some of it, and your reading will be totally wrong.
Yeah, this diagram shows it perfectly. See, to measure the current going to that light bulb, the ammeter, that's the circle with the A in it, is put right in the path. It becomes part of the road, guaranteeing that it measures every bit of current.
And get this, you don't need some huge power plant to make direct current. You can actually do it with a lemon. It's pretty amazing. The acid in the lemon acts as what's called an electrolyte. It causes a chemical reaction with two different kinds of metal, in this case, zinc and copper. And that reaction creates a voltage that pushes the electrons to start flowing. And as you can see, it produces a real, actual current you can measure.
All right, so let's do a quick recap of everything we've covered. We learned that direct current is just a steady, one-way flow of electrons. We know we can measure it in amperes and calculate it with a simple formula. And we know we can measure it for real with an ammeter, as long as we connect it in series. But most importantly, we learned that even a tiny amount of current can be dangerous and demands our respect.
So, we just saw that a lemon can make electricity because of its acid. And that leaves me with one final, kind of fun question for you to think about. Based on that very same principle, what else do you think you have sitting in your kitchen right now that you could turn into a battery?